So today we're going to talk about fluorescent resonance energy transfer. This was initially founded by Theodore Forster in the late 1940s, and it later became known as FRET. It's initially described as molecular interactions and resonance energy transfers. Forster also developed an equation that defines the relationship between the transfer rate, the interchromophore distance, and the spectral properties of the involved chromophores. Fluorescent microscopy techniques rely upon the absorption of a fluorophore of light at one wavelength and followed by a subsequent emission of a secondary fluorescence of a fluorophore at a longer wavelength. So it also talks about it's been employed to investigate intermolecular structural and functional modifications of proteins and lipids in living cells. So and one way to look at that would be using this. I'll explain that a little later. Fluorescence resonance energy transfer is a process by which it is radiationless transfer of energy that occurs from an excited state of fluorophore to a second chromophore in the same proximity. So an application of this technique, it really just transfers energy, which involves a donor fluorophore in an excited state, as I said earlier. But it needs to also transfer its excited energy to a nearby acceptor chromophore in a non-radiative fashion through a long-range dipole-dipole interaction. So I found a paper that kind of talks about what's going on and how they use the FRET method. So what this paper was asking, or what they were trying to do, is they were trying to detect the interaction of the LP1 and LP1. So the subcellular distribution of LP1 and LP1. This was in a complex in the NPL cells they saw it by the FRET microscopy and the spectroscopy. They also examined whether lipid rafts distribution can induce the NPC cells and what the relationship between the LP1 and LP1 reactions. So, in this data on the graph, it's showing you LP1's CFP and LP1 FYP in the cell. So figure 1 shows that the CN1 cells co-transfected with the CFP and the YFP plasmids. B shows it transfected with the CFB and YFP plasmids. C co-transfected with both plasmids, and all spectra were normalized as a percentage of the CFP maximal emission rate peak. So this just basically showing you, when you add the YFP, the fluorescent, you can see the LP1 more or clearer at certain wavelengths, depending on the intensity of the emission that was going on. So the findings that they found was that it works pretty well. It shows that the YFP did fluoresce a lot more than the just the normal CFP. So I have a question on whether do we think that fret could be combined with any of the other techniques that we talked about this week? Like, could we use fret with CRISPR or the other techniques that we talked about or we watched videos on with our classmates, the flow symmetry and all of that. These are my references that I used in this paper, and I hope you enjoyed this.